All right, welcome back. So the second section of chapter 3, building off of what we started with quadratic equations. Last section is polynomial functions of essentially any degree that we want to talk about. So thing to keep in mind with this section is that the characteristics we're going to talk about with polynomials apply to any degree, whether it's the parabolas, the quadratics we talked about last section, or anything with a 200th degree or 2000th degree. All of the characteristics still apply. So again, as I mentioned in my first video, please feel free to stop at any time, review things, try the examples on your own that we go through as we get used to them. Of course, get back to me and email me with any questions you might have. So the first of 6 characteristics that we're going to run through here of polynomials, again, keeping in mind every one of them has them, doesn't matter what the degree is. The first is that all polynomial functions are continuous, meaning I see no breaks, no jumps in the graph. So I'm just going to sketch a quick example, non-example of each. This would be an example of a polynomial. It is continuous across the whole graph. There is no, essentially it means that we have a domain of all real numbers. A non-example of what it would look like to be continuous would be, well, let's say I have a polynomial and all of a sudden I have a break or I have a jump. That would be an example of one of the piecewise functions we would have talked about earlier on in the semester actually, but because of this jump, this break in the graph, this is not a polynomial function. The second characteristic, moving on, that again every polynomial must have is that they are smooth curves, meaning I see no sharp turning points. So a parabola, if you think about that, is not a sharp point. It curves into its vertex and then changes direction. So a cusp is another way to describe what that sharp turning point would be. So again, a smooth curve, any number of turning points a polynomial could have. That one would be an example because at each point I have it smooths into it as it changes direction. An example of one that would not be a polynomial is one we've worked with this semester a little bit, but just to give you an example, this would be approximately the absolute value function, where at the origin it has a sharp turning point as it goes from decreasing to increasing. So again, not a polynomial if it immediately changes directions at a point there. The third characteristic that we can discuss, once again with any polynomial, is an old idea, and it's symmetry. So we can discuss symmetry also. All right, now we're going to discuss 2 types of symmetry. First one being y-axis symmetry. Now the other key piece of information to keep in mind, if it has y-axis symmetry, once again, meaning that if I fold the graph over the y-axis, it directly lines up on top of itself. Quadratic equation could do that if you picture a parabola opening upward. Not all of them, of course, but if it has y-axis symmetry, it is called, or it is a polynomial that has what we call, it's an even function. So if it has y-axis symmetry, it will be what's called an even function. If it has origin symmetry, I'm sure you can guess, this would be described as an odd function. And a note about this, when I say even or odd, what we're referring to is the degree of that polynomial. Okay, so odd or even degree, okay, meaning highest power. Okay, last thing to touch on here with the symmetry before we move into the fourth characteristic, I'm sure you notice one of them is missing compared to what we've talked about in the past. We do not test x-axis symmetry when we are talking about polynomials. Of course, this is a good question that I'd ask in class and see if anybody could come up with the answer for it. But the reason we do not test for x-axis symmetry, the title of the section is polynomial functions. If something has x-axis symmetry, that means if I fold it over the x-axis, it lines up on top of each other, which is impossible because that causes it to not be a function. So again, nice mathematical trivia that I love and math nerds love, and I'm sure you do too. So step number 4, or aspect number 4 that we look at with regard to polynomial functions, is called end behavior. End behavior. Now, end behavior is completely determined by looking at the leading coefficient meaning that is the term with the highest power. Breaks into 4 types of scenarios that we could have. First one, if we have an even function, so even degree, could be a quadratic, could be 4, 6, whatever, an even function with a greater than 0, and that's another key piece, meaning that first term is positive. What it means is that any graph with these characteristics, so again, an even degree with a positive coefficient, it means that its end behavior, it's going to extend upward towards as you go to negative infinity, and also upward as you go to positive infinity. What I want to emphasize is this is exactly like any parabola. So any even degree will always do this at its tails, okay, regardless of what happens in the middle. So you can think both directions to positive infinity, and a common example of this, of course, as I mentioned, is x squared. An example of a positive first coefficient and an even degree. That is why it extends upward to positive infinity, both left side and right side of the graph. Okay. Case B. If we have an even function with a less than 0, so meaning it's a negative. We can kind of think of the case we just did before. It means it's going to go the same direction, but this time it's going to open downward in both directions. So once again, still an even power, even degree, think of x squared once again, but now that we have a negative in front, and we knew that from last section, that means it will open downward. But again, this extends to any type of polynomial with these characteristics. So both directions go towards negative infinity, with once again a common example being the negative opening parabola. So there we go. First 2 cases with even functions, positive and negative leading coefficients. The third and fourth will be what happens at its ends if we now have an odd function or an odd degree. So if we have an odd function, once again with leading coefficient greater than 0 or positive, we have another very common graph that we can compare to this also. But once again, any function that is a polynomial with an odd degree, so 3, 5, 7, anything of that nature, as we go to negative infinity, it decreases. As we move towards positive infinity, it increases. So one direction goes to negative infinity, one to positive infinity. Once again, a common example of this, hopefully there is one that you have in mind before I even sketch it, it's x cubed. The cubic function starts off in quadrant 3, flattens out around the origin, and then extends to positive infinity in quadrant 1. So again, with a positive first coefficient and an odd degree, it will always do this at its tails. The last type, or the last case, is what will happen if we exchange a greater than 0 with a less than 0. Okay? So if odd and a negative. What this will do is take what we just did with the cubic function and exactly reflect it over the y-axis. So it will begin in the positive direction and it will continually decrease to the negative direction. Okay, so again, think of the cubic function that we just took, but flip it over the y-axis. So once again, a common example is simply the negative cubic function. All right. So again, fourth idea that we talked about, the end behavior of graphs will hold based on the type of coefficient we have, positive, negative. We've already seen how that affects things. And also, do we have an even or an odd degree? And again, something that will apply, what I always like to think is always refer back to the quadratic, the parabola, if it's an even numbered power, or refer back to the cubic function for any odd numbered power to figure out what it will do at its ends. Next, our fifth characteristic, which we're not going to spend any time looking at an example of for the time being because we've already done it, we can discuss intercepts of any polynomial. It doesn't have to be just a parabola that will have those, so we can always talk about intercepts, and these are many times called zeros or roots. So just some terms that mean exactly the same thing as finding intercepts. And our sixth and final characteristic that we talk about with any polynomial, once again, we can discuss maximum number of turning points. So how many times does a graph change direction? You can think in a parabola, that's one time. One time it goes from decreasing to increasing at its vertex. And the way that I figure this out, okay, important note here, how do I determine the number of turning points? And again, it's a maximum, it doesn't have to do it this many times. The maximum turning points is always the degree minus 1. So highest power minus 1. Think of what I just said. A parabola changes direction one time. Its degree is 2. 2 minus 1 is 1. That's why that changes direction that many times. So what we're going to finish off with here is an example of not getting too specific with the graph, but using all 6 of these pieces to actually build what the graph is. So again, sketch y equals negative 3x to the 4th minus 4x cubed. Okay, so 3x to the 4th minus 4x cubed. And again, based on the characteristics that we just talked about, how can we get a picture of what this will do? All right. So the first characteristic, the first two we discussed with polynomials being continuous. and polynomials being smooth curves, there's nothing to really test for. We understand that they will do that essentially when we sketch. We don't do anything sharp, and you can sketch a graph without removing your pencil from the paper at any point. With that, first thing we can discuss is symmetry. This is symmetry. Now, this I'm going to leave for you for the most part on your own. We've done symmetry testing in the past. This is something that I do expect you know how to do from chapter 2. Okay. Now again, if this is something you have questions on, please ask me. But the procedure, this one does not have any symmetry if you were to plug in. And once again, you do not ever have to test for x-axis symmetry. It will not have it. To be a function, it cannot have that. So again, this, refer back to chapter 2. Okay. Refer to chapter 2 specifically. You can look at section 2.1. That will tell you where the symmetry tests are. Again, this is something I expect you know how to do. This one, if I were to run both the origin and y-axis test, it does not have any symmetry. Okay, it does not have any symmetry. Step B, this is going to be an important piece that we look at from now on. What is the end behavior of this graph doing? So what does it do at its tails, remember? So going back to those 4 combinations that we talked about, determining whether the sign of the first term is positive or negative, and determining whether we have an even or an odd degree. We can assume some information about that. So what I know about this graph is that it is an even degree and A is negative or less than 0. Okay, so what I'm looking at there is -3. So pairing those together, knowing that I have an even degree and a negative first term, I know that in general my graph is going to open downward in both directions. Okay, so what this means, so again, just to kind of give a quick little sketch here, and I'm going to build a more specific graph here in just a minute or two. At its tails, I know it does this. Now the other way, and this is a nice shorthand way for you to describe this, any problems that I would give you on a homework or a quiz if we ever get to having quizzes again. This is a nice shorthand way to do it. Describe, and again, graphs we always read left to right, describe the quadrant it starts in, describe the quadrant it ends in. So this one would be quadrant 3, this one would be quadrant 4. So it is perfectly acceptable to leave your description of end behavior as such, starting in quadrant 3 and ending in quadrant 4. And again, this picture shows that. Okay, so there's end behavior, and again, I get that with the even degree and negative first term. So this one at its tails behaves like the downward opening parabola. Intercepts. Once again, this is an old idea. We know how to find intercepts. So I need 2 sets of work, one for the x, one for the y. All right, now, without doing a whole lot of work here, filling x as 0 in, I'm going to leave this to you. It's hopefully a fairly easy one to read off. If I plug 0 in for both x's, my y-intercept is just going to be 0. So that's going to be my initial point. It will start at the origin, or I'm sorry, it will not start there, but it will have a point at the origin. For the x-intercepts, once again, that means to fill in 0 for y. And all I'm going to do is use any factoring strategies that I know from here. So if you notice, what I can do, I can take out a GCF of x cubed. And to make life easier, it's always nice to see a positive first term, so let's also take out a -1 GCF with our x cubed. Okay, so that's what I'm doing. I'm undistributing, and when I do that, I'm left with positive 3x and positive 4. Okay, so again, strategies that you really need to be familiar with, and that was the purpose of the review assignment I gave before break. So what this does, now we already kind of know one of our x-intercepts. The origin is both an x and a y-intercept. So that doesn't really give us any more information. The other thing I would do is I would take this factor that I'm left with. I can go no further with it, but I get that the second x-intercept is what I get when I solve this small equation here. So I would subtract 4, divide by 3, and I would get x is equal to negative 1 and 1/3. So once again, there's a couple of points that I know. The last piece to discuss, again, this isn't really going to get this graph in particular a whole lot more specific. Some it will, but if I were to again ask you on a quiz, what is the maximum number of turning points? This is a very easy question to answer, just a simple rule to remember. The answer is 3, and it's because my degree of this equation is 4, and therefore the turning point number max number of turning points is simply 4 minus 1, which is 3. All right, so again, we have some information about the graph. It's not going to be all that specific. Now, what we always have at our disposal if we want to get more specific is to just plug in values into a table and get y values. So to finish off what I know here, I know that I really only have 2 points. I know that I have the origin being both my x and my y intercepts. I know that another x-intercept is negative 1 and 1/3, so that would be approximately here. Okay. And what you have to think of here is, at the end of the day, again, this graph is not going to be very specific, but putting together all of the information pieces we know about the graph. We know that it doesn't have any symmetry, so I'm not worried about making it perfect on one axis side or compared to another. I know that I have to open downward in both directions for this graph to work, because I can kind of do it either way as of now, unless I knew that. And then I also know it will have to have something in the way of turning points. Okay? And again, I don't know specifically how many, but it could have a maximum of 3. So again, a general graph, and this will look kind of ugly, but I'll try a little harder. It's going to do something of that nature. And again, pretty ugly, but putting together, it does fit all of the pieces that we have. We hit our intercepts, we know that it has at least a turning point, and we know that it does extend on its ends, on its tails, both directions, negative infinity. So again, with this section, it's really just knowing general characteristics of polynomials, all 6 of those characteristics. So again, to recap, they're continuous, they have no sharp points. Third, know your symmetry tests, which again refers back to section 2.1. Get a look back if you don't know how to do that. Step 4, finding any intercepts, finding number of turning points, and of course, knowing what it does at its ends. So once again, I'll be sending out a brief suggested homework assignment for this section. And again, as always, email me, contact me if you have any questions. Have a good day.